Have you ever tried asking questions to a PDF and realized it's not just text but also tables, images, and scanned pages? Most AI systems fail right there. In this video, I'll show a multi-modal RAG-based question answering system that can actually understand real-world documents. It extracts text, tables, images, and uses these RAG to produce accurate citation-backed answers. So this is our application in which we first upload the source file, then we can ask the model, and this is the response generated. If you are interested in GenAI, RAG, pipeline, or document intelligence, this project is for you. Let's get started. I am excited to walk you through a project that addresses a real-world challenge in modern AI, extracting accurate answers from complex multimodal documents. Think PDFs with dense text, structured tables, and images. To solve this, I built a multi-modal retrieval-augmented generation RAG-based question answering system. Let's talk about the folder structure. First, we have here the Chroma database, our persistent vector database. This directly stores the embedding generated from the document chunks, enabling fast and efficient semantic similarity search across the session. Next, we have the data folder, where this is the ingestion zone of the system. All the source PDFs are placed here before processing, making document management simpler and traceable. This is the ingestion folder where we extract the images, tables, and the text documents. Next, we have the QA engine. It implements the retrieval augmented generation pipeline by combining semantic search with LLM reasoning. It retrieves the most relevant document chunks and generates accurate, context-aware answers with citation. Then we have the vector store here that manages vector indexing and similarity search using FAISS for high performance retrieval, handles embedding storage, persistent and efficient nearest neighbor queries at scale. The app.py is our Streamlit application layer. It provides an interactive user interface where users can upload PDFs, submit queries, and view answers along with their citations. Then we have the embedder. It's a dedicated utility module responsible for utilizing and managing embeddings models. It acts as a clean abstraction layer between Hugging Face embeddings and the vector store. In multimodal rag.py, the core engine of the project, this file handles document loading, retrieval logic, context assembly, and communication with the LLM to generate the final answer. Let's go through the code to extract the images. To extract the images, we use fits. For each page, we locate the embedding images, convert them into PIL images, and apply Tesseract OCR to extract any readable text. If meaningful text is detected, it is stored as chunk with page number and mark them as image modality. To extract the tables, we use PDF plumber. Each table row is cleaned by replacing missing values and formatting cells into a readable pipe separated structure. The extracted table content is then stored as a structured chunk labeled as table modality. Then, to extract the text, we use fits again. Any valid page text is captured and stored with its page reference and tagged as text modality. This is the pipeline explanation. This script builds the knowledge base for our RAG system. First, it extracts the text, table, and image-based content from the PDF so that no information is missed. All extracted content is then broken into smaller chunks, which help the system to understand the relevant retrieve information more accurately. Next, these chunks are converted into vector embeddings, which allow the system to search for meaning instead of keywords. Finally, these embeddings and their metadata are saved into FAISS vector database and making the document ready for fast and accurate question answering. So next we have embedder file. In this code is responsible for converting text into numerical vectors, which allow our system to search document by meaning. First, we load our Hugging Face API token security from env file. Then we define the embedded model directly by calling the Hugging Face feature extraction pipeline. When the text is sent to the API, it returns a vector for every word in the sentence. Since we need a single vector per sentence, the code applies mean pooling, which simply averages all word vectors into one sentence level embeddings. The embed document function handles multiple text chunks while embed query creates a single vector for a user question. Finally, the text block confirms everything worked by generating embeddings and checking their size, ensuring the system is ready for retrieval and searching. Is the RAG pipeline. This script builds a complete question answering system over complex PDF using a multi-modal RAG approach. First, we load all the API keys securely and initialize a Hugging Face interface client using the Qwen 2.5 model. Next comes the PDF ingestion we use in unstructured with a high resolution strategy, which performs OCR table extraction and layout understanding while keeping memory usage low by processing via API. After ingestion, we create a custom embedding wrapper so Chroma can use our Hugging Face embedding without modification. Next them build a persistent Chroma vector database. Each document chunk is stored along with the metadata like chunk ID, content type, which later enables accurate citation. When a user asks a question, the system retrieves the top relevant chunks, combine them into a content, and send them to the LLM. The model generates a focused cited answer based only on the retrieved content. We set the max token and the temperature here. Code. We open the terminal, start the environment. It starts the virtual environment. Now, to start the UI, we type this. This is the UI of our system where user can upload document and interact with the RAG model. This streamlined based interface allow user to upload complex PDF and ask for NLP questions and answers generated directly from the source content. We need to first select the file. So this is our source file. We process the document. It takes some time. So once the document is processed, we can search anything. So this is the source file that we consider. Let's search about this image. We'll copy this. We'll search about this in our model. So here is the answer that it has been generated. Impact of the human captor, physical captor, and the combined effect, as well as the summary. We can see this is the same here in the image. That's it. Thank you.